Hello, my name is Sang Moon and I am currently PhD student in KAIST. Today I am going to talk about the paper called Energy Efficient User Association in Cellular Networks, a Population Game Approach. This paper was introduced in WiOpt conference in 2013. The user association problem mainly focuses on the decision of cell boundary users to select the proper base stations. The traditional ideal hexagonal model suggests that selecting base station which gives the maximum SINR gives the optimal performance. However, the real-life base station topology and user layout is far from this ideal model, and in this non-ideal case, when we simply select the base station which gives the maximum SINR, then the load between base stations may be imbalanced and it can cause a serious inefficiency in terms of performance. There are also some other non-trivial aspects of user association problem, which is that the good selection changes depending on the other guy's situation. Here in this figure, it is typically better to select the base station which is closest to me. But in the right figure, when there are many users near the left side base station, it may be better to select the right side base station. Moreover, there exists an energy performance trade-off in user association. When we consider cell load balancing, it often requires a higher transmission power due to the user association with far-field base stations. However, when we consider energy efficiency, then the load between base stations may be imbalanced. We can clearly know that there is a certain kind of trade-off between energy efficiency and performance, and our solution is to find the balance point between those trade-off points. In order to solve the problem, we take a game theoretical approach. The game theory describes the complex interdependence between users, and in this paper, we describe the user association problem in game framework as follows. The player is modeled as an individual user, and the strategy is modeled as selecting base station, and users selfishly select the strategy, but the other guy's behavior affects to my player function. The advantage of the game framework is that it can effectively describe the behavior of selfish individual users, and it can give an insight of designing the decentralized mechanism, which is our main focus throughout the paper. Throughout the talk, I first introduce two main modeling methodologies, and then I will introduce user association population game design by answering several design questions. Finally, I will briefly introduce the concept of evolutionary dynamics to design a practical user association algorithm and conclude the talk. First, I will explain two main modeling methodologies, which is population game model and flow level dynamics. The population game model describes the complex interplay between massive amount of selfish users. In this paper, the population or the user class is described as a set of users in a spatial domain sharing some common properties. For example, in this figure, the spatially distributed users are considered as the multiple user populations. The base station selection of each user are considered as strategy. For example, in a single population, a certain portion of the population can select a base station, and the other portion of the population can select another base station. So, when this kind of BS selection vector is given, and each base station will provide some amount of data rate to each user class, and this data rate vector is same within the user class. The given BS selection and data rate, the user behavior will induce certain amount of load to each base station, and this amount of loads will decide the payoff function of the user class. In this paper, the traffic characteristics of the user class is modeled as a flow level dynamics. The traffic characteristic is the common property in a single user class, and within the class, the traffic is modeled as a stochastic file transfer request arrival with random amount of file size. Another common properties in a single user class is that the data rate provided by the base station to user in a class. In this case, when user association happens, the flows arrive at base station and generates a certain amount of delay, which is the main metric in the performance part in our framework. Next, we move on to the game design part. I will explain the game design by answering several design questions one by one. First, the social objective. The social objective answers the question that which is the good point and which is not. We answer this question by suggesting the global optimality objective of user association problem, which is that the objective function. Here, the Y is the strategic distribution of user classes, which is the base station selection. And the phi Fy is that the objective function of flow level performance, and pi Gy is the objective function for energy saving. The details of these functions are introduced in the paper. And the eta value is the energy delay trade-off parameter, which is that the larger value of eta, the more focus on the energy saving rather than flow level performance. And the constraint is that the load of base station cannot exceed the value of 1. Next question is that how to design a good game. We can answer this question by suggesting a proper payoff function. The payoff of individual mobile users is simply suggested as a gradient function of social objective function. Here the cost function is that this denotes the marginal impact of single user on total power consumption, and the utility function is intentionally designed to make the entire society to behave efficiently. The third question is that why our game is good. This part is the main analysis part of the paper. And the main theorem in the paper is that our association game has zero price of anarchy. We can prove the theorem as follows. If the payoff function can be expressed with gradient of some function, then the game becomes a potential game. In potential game, the Nash equilibrium of the game can be characterized by the KKT condition of optimizing with the same constraint. The global objective problem is a convex program with respect to Y, thus the KKT condition is equivalent to an optimal condition. Next question is that what is the difference from other user association schemes? We can answer this question by investigating a case study, the edge user behavior in a two-cell scenario. In the deterministic association scheme is a conventional approach, which is that within the same class, the users are in the same physical situation and it will make the same decision. But however, in this case, in our population game modeling, the splitting association is allowed, and it can provide additional load balancing characteristics. The Nash equilibrium in our framework can describe this point. Finally, I will briefly explain the concept of evolutionary dynamics to design a practical user association algorithm. The evolutionary dynamics answers the question that how to reach the optimal point. The evolutionary dynamic is the modeling of gradual strategic improvement. Under some conditions, evolutionary dynamics will eventually converge to Nash equilibrium, And in this paper, we introduced 3 kinds of evolutionary dynamics. The 3 kinds of evolutionary dynamics are replicator dynamic and BNN dynamic and the best response dynamic. This evolutionary dynamics provides an insight to design the decentralized association schemes. In a two-cell scenario, we present some numerical results. This graph describes the convergence in all 3 dynamics. In all 3 dynamics, the system state will converge to Nash equilibrium. And the performance comparison of deterministic and splitting association is described as follows. When the traffic intensity grows, then the delay performance differs. The difference between deterministic and splitting association in terms of average delay grows dramatically. In conclusion, we describe the user association problem from the population gains perspective, and we intentionally designed the payoff function to make a Nash equilibrium to socially optimal point, and we consider the flow level traffic dynamics and the development of non-deterministic association schemes. Thank you.